Thanks for coming again. Seems we are dropping steadily, but that just means that those who stayed are the ones who are really interested. It's nice. So, now I talked about the Nurstrensatz problem a little bit, which is the special case of the general ideal membership problem. And here is a theorem that Ido mentioned. So if instead of trying to place 1 in an ideal generated by the polynomials f1 through fk, but a general polynomial f, then the lower bound on the degrees you are getting are actually doubly exponential in the number of the variables. That's a classical result. This 26 is 1926. And so in general, you are getting doubly exponential bounds on this version of the problem. And this bound is asymptotically tight, so you actually need degree this large. And this fact was used to by those guys to show that the ideal membership problem as a decision problem is actually exponential space hard, which makes a difference from the previous question of Nurstrensatz, where actually it was p-space, and probably we can do even better. So again, I'm interested in the circuit complexity. So here we have another question. So can you find f's such that f lies in the ideal generated by f1 through fk, but if you want to witness it, you need large circuit complexity. So as you would expect, the answer to this question is actually yes, and that's simply given by the degree bound. Because if you want to get a circuit of doubly exponential degree, you should have a circuit of exponential size. That's very simple. There is, however, a question of this. Can you prove some such thing when you are guaranteed that you can find witnesses of small degree? In other words, can you prove a lower bound which doesn't rely on the hugeness of the degree? There is a very simple case of this question that I still don't know how to answer, and assume that the ideal you are thinking about is generated just by one polynomial. So in that case, the certificate that witnesses that f lies in the ideal is unique. And you can obtain it by dividing the polynomial f by f1, which is nice, because one would think that those problems are difficult because there are infinitely many witnesses that witness the ideal membership, whereas here the witness is unique. This also tells you that the circuit complexity of G1 cannot be too much bigger than the circuit complexity of f or f1. And that's the classical Strasson's result. So if you have a circuit which can be computed using division gates, if you have a circuit with division gates of size s that compute some polynomial, you can eliminate the division gates, and it can cost you like a factor polynomial in the degree. So as long as f and f1 have small degree, then the circuit complexity of G1 will not increase too much, which is very simple. But the question then is, but maybe if you consider polynomials which have exponential degree, and now we can even think of univariate polynomials, it's not clear whether the circuit complexity of G1 could be much, much bigger than that of f and f1, which leads to the following question. Then in Strasson's elimination algorithms, can you, instead of getting the bound s times polynomial in D, which is huge if D is polynomial exponential in S, can you instead replace it by something more modest, like something polynomial in S times log D? That's one interesting case of the question. I should probably say that an open question, there's a difference between an open question and open problem in what I'm saying. So open question is something that occurred to me last night, which seems interesting. And so if you solve the problem, it will be nice for me, but it will not necessarily make you famous. Whereas open problems are things that have been considered independently. Well, it's a well, so suppose that you can really improve elimination, Chassen's elimination algorithms to give polynomial, to have bounds which are polynomial in S and log D. So then the circuit complexity of the degree of F or F1 is at most 2 to the S. So that would give you that whenever F and F1 have circuit size S, then F over F1 would have circuit size polynomial in S. And converse would also hold. So if you show that you cannot improve this bound, then you can find an example of F and F1, because in if you have arithmetic circuit with divisions, without loss of generality, there is only one division gate. It's always one polynomial over another polynomial. So this is actually equivalent to the to this question. You think the answer is no?
Yeah, because
so we have solved an open question. That's good.
I mean, I think if you consider like x to the 2 to the n minus 1.
No. Well, I don't think this works. Okay. Sorry.
Consider that there are 2 to the n many roots, right? And it has circuit size polynomial.
Yes.
Right? And then factor completely into linear factors.
Yes.
And then basically take a random subset of those linear factors and product them together.
Yes, but now what I want is to factor it. I want to write your polynomial f as f1 times f2, such that this one has small complexity and this one is big. Yeah, but x minus 1, so then x to the... It also doesn't work. I can give you a circuit, so your suggestion would be to take this polynomial, and that would be written as 1 plus x to the 2 to the n and you can recursively compute this like 1 plus x. Yeah, but a candidate like this would make me happy. So it's not clear that some easy, but on the other hand, it's not so easy to prove lower bounds on.
This particular, so if 2 to the n was prime.
If 2 to the n.
But like the second would be irreducible, right? So
yes, so you would have some small error term here. So basically, I can prove that for every a, x to the a minus 1 over x minus 1 has circuit complexity like log of a. No. It's a so this thing doesn't work. Actually, as long as you are dividing by linear function, it will never work. So, but even if you divide by x, I think in the univariate case, this thing should better have non-constant degree at least. But this is a nice exercise to compute this. If you want to do an exercise to show that this polynomial has circuit of logarithmic depth is yeah. No, I didn't. Oh, in which case? And you would be proving the lower bound or the upper bound? Or upper bound? Yeah, that's it. I tried a lot of things. I don't know. Okay. Yes, that's no, it seems like a simple question, and it's maybe like an exercise. I don't know how to solve it. definitely proving that it's impossible seems rather difficult. Designing like a clever improvement of Strassen's algorithm would be nice. The usual way how you prove Strassen's algorithm is to, if you have a Taylor expansion, then you will just truncate the Taylor expansion and at the degree that you want, and computing the Taylor expansion costs you, truncating the Taylor expansion costs you like a factor of d. An even simpler question is that if you have a Taylor expansion that you have computed, can you truncate it? What is the cost of truncating the expansion at point d? So one suggestion, which I think is what you were referring to, is instead of computing the homogeneous parts separately, is to like compute intervals of the homogeneous parts and somehow combining them. Something may be possible.
The problem is in this case you don't get rid of the terms above the degree, so that is but you get some overlap. You go over D and then there are terms which will not cancel. Check to high degree, which will cancel to just cut.
That it's possible that Amer will figure it out till the end of the talk. Another version of this problem, when you are caring about low degree, which is nice and but simple but nice example, is when you think about ideals generated by monomials. That's a case when you are guaranteed that the witnesses will have a small degree. And as an example, consider the following polynomial. It's defined in this way. And you think about an ideal generated by n+1 monomials which look like this. Now, what this somehow looks like is the permanent polynomial, which basically you obtain by taking this matrix over there, forgetting about the product over there, forgetting about the z's, and taking out of it only the products in which you have never picked one variable from the same column. Now there is a very simple observation, and that first of all the polynomial f lies in the ideal generated by z, and second of all that the complexity of witnessing that f lies in the ideal generated by z is at least the complexity of the permanent. So you get here at least a conditional lower bound, assuming that permanent is hard. Then f and z, they all have quadratic circuit complexity, but if you want to witness that f lies in the ideal generated by z, you will get, say, exponential complexity, assuming that permanent requires exponential circuits. It's a very simple proof. So if you want to show that f lies in the ideal generated by z, you just open all the brackets, you collect all the terms that contain the product z1 through zn, and if you think about it, those are exactly the terms that correspond to the permanent. Those they correspond to permutations. And the other terms that don't correspond to permutations are the terms that in which you have multiplied, let's z1 by z1 or z2 by z2. So those are the terms in which you have zi squared for some zi squared. And to show that the complexity is at least the complexity of the permanent is also very simple. I will leave it as an exercise. Basically, you will show that this is pretty much the only thing you can do. That's the proof. But it's really an exercise. Now, Tony has covered polynomial calculus, so I will not talk about polynomial calculus. I'll skip it. Just I will mention again what Tony has already explained, is that Nullstellensatz has been considered as a proof system. So this is the equation we have seen before, except usually in proof complexity you think about it in a different way. So first of all, you always or typically you have the Boolean axioms that tell you that you are thinking about the 0-1 solutions, and the polynomials f usually are low degree polynomials which correspond to CNFs, and you are thinking about witnessing unsatisfiability of a CNF. What I was talking about before was a different measure. So the measure you care about is the degree. That's the traditional measure. Tony also mentioned her version of the system, which is what I was describing before, is that you care about the arithmetic circuit complexity of the witnesses G. There should be GK over there.
The result of the previous slide about the determinant, the circuit is at least determinant complexity. So this gives you a Munch term that's a lower bound except without the Boolean axiom.
Well, unfortunately, you are placing there the point was that you have a polynomial f that you are placing inside an ideal. It wasn't that you are placing 1 inside the ideal. It was a conditional result, assuming that VP is different from VNP, then you have a result. And probably one should be able to find so it's a conditional lower bound on the ideal complexity of f with respect to z, and I don't know how to do the lower bound when f is replaced by 1, even conditionally. I wouldn't be surprised that a simple trick like that could work there also. One can get some lower bound on the question when instead of placing 1 in the ideal generated by z, you will be placing 1 in the ideal generated by z and f minus 1. In that case, you will get some lower bound, assuming that the polynomial that multiplies f minus 1 doesn't have too large degree. So it's even more conditional than this conditional bound. Yes, sorry.
I mean, but if you could put 1 there, I mean, I guess this is fast forwarding, but if you could put 1 there, then Tony and Josh showed that Frege is simulated by this Hilbert system, and then if you got a conditional lower bound saying that permanent is hard implies, you know, this complexity, this proof complexity is large, then I would get a lower bound for Frege.
No, that's maybe that's that's the good point. I should have emphasized that. So it's not only that, but the Boolean axioms are not there. That's the main thing. So if you edit like the Boolean axioms, then it becomes trivial, sort of. So that's polynomial calculus. Sorry about that. And I will be talking about the Boolean ideal. So far I was talking about ideal which didn't contain the Boolean axioms. So the Boolean ideal is simply the ideal generated by the polynomials xi squared minus xi. The nice thing about those polynomials is that they already form a Grabner basis of the ideal. So like often with those ideals, you would think that you will spend a lot of time just finding the Grabner basis. Here you already have the basis, but still the problem is sort of non-trivial. But the version of Nullstellensatz that you can show in this case is the following. So if you have a polynomial that vanishes on the Boolean cube that's is equal to 0 in every Boolean ideal assignment, then it lies in the ideal generated by xi squared minus xi. And moreover, you can witness this by polynomials of quite a small degree. And this is a special case of the combinatorial Nullstellensatz where instead of thinking about Boolean, anyway, let's not go into that. It's a special case of a more general theorem. To prove this is very simple, and okay, so I will prove it so that we have at least some proof. It's rather obvious, yes? So It's related. I will mention it later. So there is one. I will mention it later. I actually was anticipating this. So yes. So I will give you a proof. The reason why I'm giving you a proof is that I will later extend the proof. So you want to show that f vanishing on the cube, you can actually place it into this ideal. So you define polynomials f0 hat through fn hat and g1 through gn. Those will be the witnesses. So we will start with f hat 0 to be equal to f. And then supposing we have already defined f I minus 1 hat, then you define gi and fi hat in the following way. So you divide f I minus 1 by xi squared minus xi. You think about it as a univariate polynomial. You divide it, and at the end of the division you end up with a polynomial that is linear in xi. So that will be your fi hat. So it's a polynomial which is linear in the variable xi, and gi is the other thing that you have obtained in the division. So you can clearly see that you can express f in the following way. And finally, you can see that the polynomial fn hat that you were left with is multilinear, because that's how you construct it. You have consecutively multilinearized your polynomial with respect to all the variables. It's equal to f2 on the Boolean cube, and hence it must be identically 0. So here I'm using the fact that if a multilinear polynomial vanishes on the cube, it must be 0. So that's a simple proof. And there is another open problem which looks pretty much like the ones we have had before, except now it's an open problem instead of an open question. So you want to find f that vanishes on the Boolean cube, but the complexity of witnessing that f lies in the Boolean ideal is large. I don't know this answer modulo any assumption.
Is it clear that there exists an f, or is it that?
No, I don't know whether there exists an f. Well, I don't know it. And there is an assumption modulo this, like assuming that, let's say, coNP is not equal to NP, or coNP is not equal to NP with an advice from a PIT, then the answer should be yes. But in fact, this is the question which is related to the results of Tony and Grochov, which relates this question to the lower bounds on extended Frege, which I will try to explain.
So if f is an unsatisfied CNF,
Yes.
so its multilinearization should be 0.
0, yes.
So it doesn't say anything about if the GI is.
But I think that's how the expected answer is yes. I think that's what you're saying. Right?
I mean, just
Like knowing, so if you give me any answer to this question, which is modulo some assumption which is not really related to coNP versus NP, then I would be impressed.
yeah, no, I'm not interested.
This is actually stronger than extended Frege law.
Yes, I'll be explaining it now. In particular, if you could prove this question, solve this question under like assumption from circuit complexity, like for example VP is not equal to VNP, then I would still be impressed. So the example that I gave you before about this ideal generated by the polynomial Z, it was intended to show you that maybe if you use assumptions like VP is not equal to VNP, then you can actually tackle problems of this kind. In this case, I don't know how to do that because obviously this Boolean ideal is behaves in much weirder way than this monomial ideal that we had before. But still, it's not clear that if you assume that permanent is hard, then you can play with this question a little bit, and maybe you will get some conditional lower bound out of it. But I don't know even how to do that. Like one issue here is that there are infinitely many witnesses, and then you don't know exactly how the witnesses behave. Even though in the previous example there were also infinitely many witnesses, but somehow they were much better behaved. For me, the main issue with this ideal is non-homogeneous. That adds an extra problem. Yes. Yes. Or which one? Oh, sorry. Yes. Yeah. Sorry. That should be. Yeah. Yeah. Obviously, the polynomials G1 through Gk. No, the G1 through Gn. They witness the fact that f vanishes over the Boolean cube. Now I'll be roughly explaining what I think are the main ideas in a paper by Grochov and Pitasi, which I think roughly tells you that if you prove certain proof complexity lower bounds, then you will get circuit complexity lower bounds, or in other words, that certain proof complexity lower bounds are at least as hard as circuit lower bounds. I will deviate from the paper to some extent. The major open problem, I think, in proof complexity that Tony has mentioned is to prove superpolynomial lower bounds on the Frege or extended Frege systems. In case we are still unclear what Frege and extended Frege is, we can just... It's actually, again, a high school propositional logic system, at least the Frege system. And this system, the best lower bound we have is for bounded depth Frege. It's a Frege system which uses circuits or formulas of bounded depth. In the De Morgan basis, it's open even for bounded depth Frege with parity gates. But how is it now related to the ideal membership question? So first I will tell you how to understand a Boolean circuit as an arithmetic circuit. So given a Boolean circuit A, you can define from it a polynomial which you define in the obvious way so that you translate the circuit gate by gate. So conjunction you replace by product, negation by 1 minus U, disjunction in a more complicated way, but let's say we have just conjunctions and negations. The somehow obvious thing about this translation is that the polynomial and this original Boolean circuit, they agree on the cube. They have the same circuit size. In the first case, it's a Boolean circuit. In the second case, it's an arithmetic circuit. And another simple observation is that if you take a translation of a Boolean circuit, then it's easy to witness that the Boolean that the polynomial takes only 0, 1 values on the Boolean cube. Those are very simple facts that are easy to verify. Now, one thing about the translation that I'll mention, which is rather technical, is if you consider the case that you have a circuit or a formula which is just a conjunction, then the translation is just a product of the individual conjuncts. So for example, if A is a 3CNF, then you will get a product of degree 3 polynomials in the translation. Now, saying that A is unsatisfiable, meaning that there is no... Yes. Meaning that the CNF never evaluates to 1, means just saying that the polynomial, which is the translation of it, lies in the Boolean ideal. That's trivial. There is a different way, however. You can say that A is unsatisfiable if and only if you can place 1 inside the ideal generated by the Boolean axioms and the translation A1 minus 1, AK minus 1. Because if A is unsatisfiable, it's impossible simultaneously for all of those things to be equal to 1. That's a different way how to think about it. What I'm saying it mainly for the reason that it doesn't matter in this case. So those two quantities are polynomially related. They differ at most by an additive factor. And that was the question that Tony asked before, because often it's more common to work with this formulation of this problem rather than this formulation. But as long as you are working with polynomials which come from translations of a Boolean circuits, then there is really no difference between the two formulations. And I am looking at this formulation only because I find it a little bit more intuitive. But if you prefer this one, you can look at this one as well. Yes? So, and here is the thing that relates this question to extended Frege. And it says that if A has an extended Frege refutation of size S, then the cost of placing this polynomial A star into the Boolean ideal is polynomial in S. So if you don't know what a Frege system is, this is the only thing that I will really use about extended Frege. So what this means, well, it means that if you want to prove, if you manage to prove lower bounds on this ideal complexity with respect to the Boolean ideal, then you will get proof complexity lower bounds on extended Frege. So this is one way how to obtain from circuit lower bounds proof complexity lower bounds. That seems nice. But here is a different proposition, which is the following. So assume that Vp is equal to Vnp. Then whenever f vanishes on the Boolean cube, then the ideal complexity of f modulo this ideal, the Boolean ideal, is polynomial in the circuit complexity of f. So in other words, you can never prove a lower bound on the ideal complexity unless you have first proved that Vp is not equal to Vnp. So if you want to prove extended Frege lower bounds in this fashion, you first have to prove circuit lower bounds. I should emphasize again, I'm here deviating from the way how the paper is presented. I will then mention later again how it's actually done in the paper. Yes, I will tell you. No. Yes. So that's a good point. So I told you before about this Boolean Nullstellensatz that there always exist witnesses. So if you assume that A star has a small degree, so let's say it's a translation of a CNF, then there will always exist polynomials of small degree which witness the ideal membership. However, if you are going, if you want to extract those witnesses from extended Frege proofs, there is no guarantee that they should have polynomial degree. So theoretically, it might happen that every witness of polynomial degree must have exponential size, but there might exist witnesses of exponential degree of polynomial size. So in extended Frege, you cannot assume that there is a low degree. In a Frege, you can, because you're dealing with
You
formulas.
don't know how to refute this scenario that you described, right? That,
No.
It's probably not true. I mean, it's impossible to get a bound on the degree of extended Frege.
No, if we could do that, yes, we could. If we could do that, we could probably simulate extended Frege by Frege or with a modest cost. So it's very unlikely that the circuits G that you get, you would have small degree. Probably you really need exponential degree. Does it still make sense?
you really expect that exponential degree series that will not be squashed down.
Well, I'm not sure. So for me, proving a lower bound, even under the assumption that the degree, I told you that the degree is at most d minus 2, let's say. Even if you prove lower bound for this, I would be impressed again. But that wouldn't really imply anything as far as...
In this case, is not like proving something super interesting.
Well, it would still imply that VP is not equal to VNP. That would still be cool.
Yeah, hard to explain. It's hard to explain.
No, but okay. So again, like those lower bounds, I think are interesting even conditionally. So assume that permanent is hard, then you will still impress me if you prove lower bounds, assuming that the degree is polynomial. That still would be great. So I'll give you now. So proposition 4 is this implication that if VP is equal to VNP, then you cannot really expect meaningful lower bounds on the ideal complexity. So I'll now sketch you the proof. So assume that VP is equal to VNP, and now we want to witness that F lies in the ideal by G's which have small circuit complexity. Now, I will cheat a little bit. I'll assume that F has polynomial degree because it simplifies things a little bit, but it's not too much of a cheating because in reality, the F that we would be interested in is a translation of a C and F, hence a formula, and hence it would automatically have polynomial degree. But dealing with exponential degrees of F is a little bit, just a little bit more tricky. Now, if you still remember the construction of those F heads, so you were successively multilinearizing your polynomial. You were reducing, you first multilinearized with respect to x1, then x2, etc. So, in other words, the Fi head polynomials that one obtained had the property that they were multilinear in the first I variables, and they agreed with your polynomial on all 0-1 assignments to the first I variables. So that's what the polynomials Fi had satisfied, which means that you can write Fi hat as a very simple Boolean sum over the polynomial f. So since Fi hat is multilinear with respect to the first I variables, it's uniquely determined by its values on the Boolean cubed on the first I variables. So you can uniquely write it in the following way, where alpha is this polynomial. The reason why you choose this alpha, which looks weird, is that if you take an assignment, a Boolean assignment to the variables z and a Boolean assignment to the variables x, this polynomial is equal to 1 if those assignments are the same and is equal to 0 otherwise. That's the only role of the polynomial alpha. So it picks the right terms from the polynomial f. So what I'm just saying is that if you write Fi hat in this way, it guarantees that Fi hat and f have the same values over the cube when you take inputs from 0, 1 to the I. And now, well, this looks pretty much like VNP. Now we have a Boolean sum over a small circuit. So if you assume that Vp is equal to VNP, then Fi hat actually has a small circuit. And now, if you still remember how GIs were obtained, they were obtained by taking fi hat minus fi minus 1 hat, dividing it by the polynomial xi squared minus xi. That was the definition. If you still remember the Strassen's elimination algorithm, then this GI is a polynomial. You have computed it using one division gate. You can eliminate this division gate with like a modest cost. And that's the end of the proof. Modulo the assumption that f has a polynomial degree. But I should tell you that if f doesn't have a polynomial degree, you do something slightly different. It's really easy to see that in the case of the division algorithm, I told you before that it costs you a factor of the degree if you use Strassen's elimination. And f can have exponential degree, that wouldn't really work. But it's easy to see that in this particular case, you don't have to use elimination algorithm. You just prove that whenever this thing is divisible by that thing, you can just compute it by a constant factor of increase in the size of the circuit. So you don't lose a factor of the degree, just a factor of 5 or something like that. Yes, but then you still have to argue a little bit more, because now it's a Boolean sum over a polynomial of exponential degree. So but you would first play with it and first change it into polynomial of low degree and then do something. So that was proposition 4. Proof of proposition 3 is by induction. It's by a straightforward induction, but I would have to explain what exactly extended Frege is. But maybe if you remember the circuit PI system, and I told you that extended Frege you can obtain sort of by adding to this circuit PI system the Boolean axioms, then the proof would become sort of clear. So I will skip the proof of proposition 3. Well, and there is a theorem that one can sort of gather out of it, but I think that the two observations, proposition 3 and 4, were sort of interesting enough, but you can collect them into this theorem, which says that, so suppose that extended Frege is not polynomial bounded, and suppose you think over GF2, then one of two things must happen, that either VP is not equal to VNP, or there exists a circuit such that the polynomial associated with this circuit is identically 0, but extended Frege cannot find a short refutation of not A. Well, this looks maybe a little bit unclear, but let me say that the circuit that you are given is not only unsatisfiable, it vanishes over the Boolean cube, but it also vanishes on the algebraic closure of the field. So it's a polynomial identity. But extended Frege still cannot prove that it vanishes even on the cube. So in particular, extended Frege cannot simulate an algorithm for polynomial identity testing. So not only it cannot prove efficiently polynomial identities, it cannot even prove that a polynomial identity vanishes over the Boolean cube. Well, and you can also replace this assumption by this, that the circuit PI system is not polynomially bounded. That's the system we had before. And in the paper, the reason why I picked GF2 here is that extended Frege can directly talk about GF2. If you want to think about different fields, then you can assume replace the second assumption by the assumption that extended Frege cannot prove correctness of a PIT algorithm in some exact way, which I will not explain. Here is a sketch of a proof, but it's just an observation. So, like, assume that 1 and 2 don't hold. You want to refute. let's not go through the proof.
So you wrote it CPI, so it's the proof, the syntactic proof of polynomial. But this is different than because the approach of
Uh,
the second set 2. Second 2?
yes, the second two.
Yeah.
Well, it's a direct observation. So, like a well, okay. Let me show you the proof. Okay. Now here's a typo. So suppose you want to so this A is not the same A as this one. Okay. So assume that 1 and 2 are false. And suppose you want to find a refutation in extended frag, and it really doesn't matter that it's extended frag and can be like almost any other system. And you want to show that the formula A is unsatisfiable. So you will just guess the witnesses G1 through Gn such that this is a polynomial identity. Now, if Vp is equal to Vnp, then those G's will have small circuit. And now, if 2 doesn't hold, it means you can actually prove this identity efficiently in extended frag. So now you have proved this identity in extended frag, but now you can easily get out of it a proof that A cannot be satisfied on Boolean cubes because of those axioms. And this is not a typo because we are working over GF2. It's a good thing. So, still makes sense? So this is just, mainly an observation. So now I was trying to explain like the most interesting ideas, I guess, in this paper, but I should say more about how what they actually do in this paper. So they, among other things, they prove the superpolynomial lower bound on number of lines. They prove this theorem. So polynomial calculus, usually you are trying to find lower bounds on the degree or on the number of monomials that will appear in polynomial calculus. Here you show that a lower bound on the number of lines in polynomial calculus implies circuit lower bounds. Here there is a word skew arithmetic circuit. So a skew circuit is just a circuit where in a product gate at least one product has degree 1. It's basically the same thing like it is the same thing like an algebraic branching program, if you know. But moreover, because of it's up to like a quasi-polynomial, it is the same thing like a general circuit. And the only reason why in this theorem you obtain lower bounds on skew arithmetic circuit is just, if you recall the polynomial calculus definition. So there, from a polynomial G, you can infer polynomial alpha times G, where alpha has degree at most 1. That's where the skewness in this theorem comes from. Just to give you some idea. And now I'm almost done. Also, they defined a different proof system, which they call the IPS system, and that's defined as follows. You want to show that polynomials don't have that a set of polynomials doesn't have a common 0, so you witness it by a polynomial G, which depends on the original variables x and on auxiliary variables y1 through yk, which correspond to the polynomials that you are dealing with. And you have two properties, that if you plug for the variables y0, you get a 0, and if you plug them for f1 through, if you plug their f1 through fk, you get a 1. This clearly shows that the polynomials cannot have a common 0. And it's almost the same thing like the version that we have considered before in the Nullstellensatz. if you manage to write 1 as f1 g1 plus blah 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 fk gk, then the IPS certificate will be just the polynomial g when you replace f1 through fk by y1 through yk. So what I was talking about so far were like a special case of the IPS certificate which is linear in the variables y. Yes. Like both those conditions are equally important. Oh, oh, sorry. No. How much overtime am I? 2 minutes. Also, typically, because we are dealing with proof complexity settings, so you consider this in the case where your polynomials are translations of a CNFs and they contain the Boolean axioms. Well, and finally, so this is what I think are the highlights of what was shown. Is that if you prove superpolynomial lower bounds on the IPS certificates, then you will get VP is not equal to VNP. I've already shown you the proof because I was considering linear certificates which were linear in the auxiliary variables y1 through yk, which is a special case of the general certificate. So we have already seen the proof. You have already seen the inductive proof that, again, the linear certificates simulate extended Frege, so the same must be true for IPS, which seems stronger. They also shown that extended Frege actually is equivalent to IPS, provided that extended Frege can prove efficiently polynomial identities. And they also shown a lot of versions of those statements when you restrict yourself to bounded depth circuits and several other classes of circuits, which seems to be interesting because we don't even have lower bounds for bounded depth Frege systems with, let's say, parity gates. So obtaining lower bounds for this IPS system or for this ideal complexity, as I was calling it, when you restrict the witnesses to have bounded depth, that would still be interesting because we would obtain lower bounds for Frege of bounded depth with, say, parity gates, which is still open. And I think this is...
I also want to ask again about the degree. What happens? Do you assume anything about the degree of the circuit G, or now you allow exponential degrees, right?
I don't...
of course, it would be interesting to prove lower bounds even if you bounded degrees, but the simulation will give you...
Well, so in the IPS there are two sets of variables. There are those y's, there are those x's. So as far as I can see, the y's without loss of generality can have degree 1. So I don't care about the degree that you can get down. But the degree with respect to the x's, I don't see any a priori bound on the degree. But so again, proving lower bounds on Frege, which is still cool, or bounded depth, it's small degree. But I don't think you can a priori put any restriction on the degree.
I'm just asking because I'm so used to thinking about polynomial
Yes,
degree,
I know.
just want to make sure that
Yeah, it's...
putting more assumptions in it.
But it is exponential upper bound.
well, okay, yes, an exponential upper bound. So it's at most exponential.
It's exponential influence.
Well, so that's the end of my talk. But